Okay, good morning, everyone. It's a pleasure to have Emilio Minicello um, giving a mini series in three parts um, entitled Coverages and Grothendieck Toposes. Thank you, Emilio.
Thank you, Mahmoud. So I want to say a couple words about this right off the bat. Um, so I recently finished my PhD under Mahmoud. And during that time, I tried to learn sheaf theory. And one thing that I struggled with sheaf theory was going between coverages and Grothendieck topologies. Um, And so I wanted to dig into that relationship a little bit more deeply, because there's an example that comes up in my research and Mahmoud's research, other people in this call's research, where they need to use um, a coverage that doesn't come from what's called a Grothendieck pre-topology, which is something that's more common in the literature. So that led to these set of notes, and they're on the archive. So it's by the same name. I've dropped a link in the chat to these notes, and I'm really excited to talk about them here. I worked on them for a really, really long time, um, and so yeah. So let's get started. Um, so first definition is let C be a category and U in C, a family of morphisms over U consists of a set R, Ri, Ui to U, I and I. So this is how I'm going to be going through this talk. I'm just going to write out definitions. I'm going to follow my notes pretty closely. So if you want to follow along, my notes are on the archive, so you can take a look at that while I'm talking. So um, so we have C as a category, and we have a fixed object U. A family of morphisms over U is literally just a set of morphisms with codomain U, and we use I as the indexing set. Okay. And if you have any questions, please feel free to shout them out. Okay. Now, given um, two families of morphisms, R and T, which all denote T lower J, VJ to U, J and big J, a refinement F from R to T consists of a set function alpha from I to J and morphisms Fi from Ui to V alpha I such that the following diagram commutes. So you have Ui, Ri, U, V alpha I, and T alpha I, and Fi. Okay. So this is the idea of a morphism between families over a fixed object U. It means that for every index I of this family, I choose something in J, and then um, this triangle has to commute. Another way you could say it is that every Ri factors through some TJ in J. Okay, so this is a refinement.
Or
So
equivalently, that I'm working in sliced over U
yeah,
morphism.
exactly. Um, so an example,
So which
uh,
one is a refinement of which one then?
so this is a refinement. You typically say R is a refinement of T. Okay, so let me give the basic example for where this notation comes from. So this is going to be kind of the Uber example throughout all of these notes. So fix the topological space.
Yes.
A little counterintuitive because R can be a subset of T, but still called a refinement.
R could be a subset of T. Yes. Yeah, exactly. Yeah, that's fine. Um, counterintuitive. I see what you mean. Yeah, because I haven't talked about covers yet. Yeah. When
Okay.
we talk about covers, then it'll be more intuitive. But yeah, so let me just talk about that right now. So fix a topological space X and let curly O of X be the poset of open subsets of X. Okay. So if I have U and V open subsets, then U is less than or equal to V if and only if U is a subset of V. So this is a category whose objects are the open subsets of X, and there's a unique morphism from U to V if and only if U is a subset of V. Okay.
You just, yes, you've rewritten the curly less than symbol as a sharp less than symbol.
Exactly. So now, if I have a whole bunch of UIs, including into a open subset U, call that curly U, and then I have a whole bunch of VJs, including into U, call that curly V, I is in I, J is in J. Then a refinement looks something like this. So maybe VJs cover it like this. And it doesn't have to be a cover, right? We're just talking about families of morphisms. So maybe I have V1, V2, V3, V4, V5. Then each UI just has to be a subset of these guys. So maybe we have something like U4, U7, U6, right? What couldn't happen to be a refinement is something like that, where it doesn't land completely inside of one of the VJs. So then the function here would be some on the indices would be something like send 4 to 1, send 7 to 5, send 6 to 4. Okay, something like that. So this is the most simplistic situation, and this is what we're going to attempt to generalize as we go along. Okay.
It might be worth mentioning that it looks more like what you naively call covering if you had inside, let's say, V1, more than one thing landing.
You had more than one thing landing. What do you mean by
Right.
that?
Instead of saying V1, you had only one open set that was inside of V1.
Right.
But I could have had a many one function that, let's say, put two open sets inside of V1.
Absolutely. So I could have something like,
Then it looks more like what the naive notion of covering,
right.
to answer Mahmoud's objection.
Okay.
That would be a
Good.
case
Mine
of
was also that it doesn't have to be like,
yeah,
yeah,
yeah, not yet.
objects may not be hit or
Exactly. Exactly. Now, given a refinement f and alpha is the underlying function on the index sets, we call the morphism Fi from Ui to V alpha I, the ith component of F, the refinement. Okay. We write R is less than or equal to T if there exists a refinement F from R to T.
So
So
it's a property, it's not structure.
So this is property, this is structure, right? So we're going to go back and forth between this idea as we go along. Okay. Um, so uh, let so for fixed so for fixed U in a category C, let fam over U be the category whose objects are families over U. So I'm going to drop saying families of morphisms. I'm just going to say families over U. And morphisms are refinements. Okay. So some examples. So given any category and any object, there are families. There's the empty family. There's the empty family. And there is the maximal family. I call that Y of U. And this is just a set of all maps to U in C. And later on, we'll see why I use this notation for this. Okay. We sometimes.
hello.
Yep. Hello.
I just want to say I like to think about partially ordered sets. So
Yeah.
That category C certainly can be a partially ordered set.
Sure.
And that would include the preceding example of the open sets of topological spaces.
Yep, exactly.
Thank you.
No problem. If a family consists of a single element, we'll sometimes write it like this. Okay. All right. Now, given a family T, Vj to V, and soon I'm going to start abusing notation and leaving out indices and stuff. So just be aware of that. So given a family over V and a map G from V to U, let G lower star of T be the set of maps of this form. So it just takes every morphism in the family and just pushes it forward by post-composing with G. So we call this the push forward. T by G. Okay. And then similarly, R from Ri, Ui to U let G upper star of R be the set of maps F from W to V such that GF belongs to R. And this is the pullback. R by G. So what does G upper star R look like? So F is in G star upper star R if I can factor it. So I have F. Whoops, that's not what I wanted. And then I have G. And I want this thing to belong to R, so it has to be some Ri. Okay.
So the picture of a pullback is a square, it's a triangle, not a square, right?
Yeah. Yeah, exactly. It's all the things that when you post-compose by G, they land in R. Okay.
So usually for pullback, you also have like a domain map, but here you're not doing that.
That's right. That's right. Okay, good. Now, yeah, so sorry, the beginning, the first talk here is probably going to be very definition heavy.
This is perfect. This is just go with the same pace. Yeah.
Good. So now we're going to talk about collections of families, and I'm going to have to restrict to small categories. And the reason for this is very important, and I'm not going to talk about it too much today. Maybe I'll start next lecture talking about set theory, okay? But let me just start off by saying for the rest of this lecture, all the categories that we're going to put structure on are going to be small. And then next time we'll talk about what happens when you want to talk about regular categories, large categories, and what do we need to be careful about. Okay. So first, let's go with this. A collection of families J on a small category C consists of a set J of U consisting of families over U. We write R in J to mean that R is in J of U for some U in C. Okay? So all this is it says for every object in my category, I have a set of families over U. That's just what a collection of families is. Now, we want to say what a coverage is. So this is going to be the main object of study for us.
Sorry, so
the
for
rest of the
every object you need, one family or many families?
many families, the set of families.
Let me just read that.
J views a set of families.
But it can be empty.
It can be empty.
And each of the elements of that set can be empty. If there are elements, each of the elements can be empty.
Exactly. Exactly. So you can already see that this is quite general. Okay. Definition. So this is the main object we're going to be studying. We say that a collection of families J on a small category C is a coverage if it satisfies two conditions. So I'm going to write these conditions and then I'm going to explain a little bit more what they mean. Okay. So the first condition, we ask that for every U in C, the singleton family given by the identity on U. So let me maybe write it like this. So this consists only of the identity map is in J of U, and another condition that says for every U in C and map G from V to U in C, there exists a family T in J of V such that um, G lower star of T refines R. So let that sink in for a second, and then I'll explain what it means.
I'm missing the quantification of R in axiom 2.
That's right, because I didn't write it. Thank you. For every R and every U and every R and J of U. Sorry, let me just rewrite this a little bit better. So it says for every U in C, every R in J of U, and map G from V to U. So I'm quantifying over U, R, and G. So for every, that's not the right button. For every U, R, and G, there exists a family T such that this condition holds. So let me explain what that means. So suppose I have an object U, and I have a family R over U. Now, if I have a map G from V to U, it says that there exists a family T over V such that the family I get when I take this family T and I post-compose it with G, this new family here is refines R. So that means that there exists a function. So how about we write it like this? If I have G lower star of T, so that always looks like Vj to V to U, and that has index set J, then there exists a function alpha from J to I and maps S J from Vj to U alpha J. So I get maps like this such that the diagram commutes.
Hey, Emilio,
Yeah,
is the somewhere in here saying that the push forward is also now in J of U?
no,
Okay, thanks.
no, no, it's a good point. So what is this saying? It says, okay, I have you, I have a family over you, and I have a map. Okay. The first thing you might think of is, oh, I want to take that family and I want to pull it back to V, right? And then I want to see that that's a family over V that I'm considering. But not all the categories that we want to consider as we go along have pullbacks. So this is like the next best thing. And this works for any category. It makes sense in any category. So it says, I have a family over you. I have a map. Maybe I can't pull it back because I don't have pullbacks. But there exists a family over V and a refinement of the resulting family. Okay. So let me know if this is confusing because this is kind of the key property here.
But
And
there's
my
no universal property here.
I'm sorry.
well,
There's no universal property like a pullback.
There's
yeah, I
no
mean,
universal property. It's just an
right,
existing statement.
right. In particular, you said that the S all there has to be is a map as J that does this
Exactly.
kind of thing. And no, he did not. It was not required to be unique as in universal property.
Exactly. Exactly. So it just says for every J, there exists a map making this diagram commute. Okay, so it has to just land in some U alpha J.
Can I say something? I
Okay.
just to I know a little bit about Grothendieck topologies, but I want to see whether I have built the right intuition about this. So you have the covering UI and the map from V to U. So suppose in your categories you have pullbacks. Okay, you pull back the first covering, but what you have here, TJ, is a refinement of the pullback. So you might
That's,
not have the pullback itself, but you have a refinement of that. Is this a good way to look at it?
that's a great way to look at it.
Okay.
Yeah.
Oh,
And
oh,
then and we'll talk about how pullback, if it does have pullbacks, what does that mean? We'll talk about that in a little bit. But yeah, that's a good way to think about it.
okay. Thank you.
Welcome.
Why can't someone always say that, oh, you can satisfy this trivially by choosing like VJs to be empty?
Chooses to be
Well,
so
and what is a map out of an empty set? You know,
So, okay, so,
the target has to be empty, right? I can only
no,
map out of
no,
an
no,
empty
no,
set.
oh,
no, no,
no.
no. No, let me say so. Suppose we're talking about topological spaces, right? So
Yeah.
then this would be an open subset, and this would be a subset of U, right? And then suppose that V was empty, right? Empty
Um,
set,
Yeah,
huh?
I'm saying suppose, no, choose VJ to be empty.
So if you choose VJ to be empty, there's always a unique map here and here, making the diagram commute because it's an initial object, right?
But I'm
Um,
saying that wouldn't that like, because that would work for anything, wouldn't that make two obsolete?
so but you want this to be in J.
Right. So the map from empty to that better not be included.
Right. J had to
Yeah.
have the whole V, but it didn't have to have none of V.
So inclusion, as when the inclusion of empty to every object is part of your structure, then this is kind of obsolete.
Exactly.
Yeah.
So we're going to talk about a whole bunch of really dumb coverages you can put on any category,
Okay.
right? So yeah, so you're spot on. The point is that what you want to do is you want to restrict these J's to be things you care about. So like the most obvious example is going to be coverings.
Yeah.
Okay. So sure, the empty set includes in, but if it's a cover, then V is empty, right? And then yeah.
Okay.
Okay.
Thank you.
Good. No problem. All right. So this is the definition of a coverage. It works for an arbitrary category. Let me say briefly, this condition is not completely necessary. We could probably get away with the theory by not requiring this, but it makes the theory easier, and I can't find an example where it doesn't hold. Um, so we include this first condition. Okay.
Why not have the example where you have to every object you assign the singleton family, where the only element of it is the map from the empty.
Not every category has an initial object.
Ah,
Right. Um,
I see.
okay. So if J is a coverage, then we call the families in J of U covering families over U. Over U. If a map Ri from Ui to U belongs to some covering family R, we call it a covering map. Call it a covering map. This terminology is not super standard in the literature. In some of Duggar's papers, he calls them basal maps. I don't really know why. But if uh, if C is a small category and J is a coverage on C, we call the pair CJ a site. Okay. So this is also kind of the main object we're going to be studying here. We're going to be studying sites. So originally, sheaves were defined by Jean Leray over the site of open subsets of a topological space where the coverage is given by open covers. And I'll explain that example in more detail in a second. So Jean Leray, while he was a prisoner of war during World War II in a German war camp, he didn't want to work on PDEs, which was his main subject, because he was worried that the Nazis would be able to take advantage of his analytic.
Well, even worse, they were PDEs in hydrodynamics, so they were quite close to engineering.
So that could have been really, useful for them. So he didn't want to work on that in prison, worried that they would be able to take advantage of it. So he decided to work on topology, and he came up with the idea of sheaves there.
And by the way, he was secretly doing the other thing because the way he wanted to solve his PDEs was by using contraction mapping theorems. So you needed to develop topology of influential spaces anyway.
Right. And so then that theory of sheaves went on for a long time as just sheaves over topological spaces. And then eventually, Grothendieck, in his desire to solve the Weil conjectures, realized that he needed a cohomology theory that didn't work as cohomology over a topological space. And so he came up with the idea of a Grothendieck topology, or a site. So what we're doing now is generalizing that notion. And so what he did was he came up with the notion of a Grothendieck topology in a site, notion of sheaf cohomology, and he was able to come up with the Attal site and then define cohomology for that. And with that, he was able to, other people along with him were able to solve the Weil conjectures using that cohomology. So that's kind of the historical background. So Grothendieck topologies were used for a very long time, but then I think Johnstone invented coverages. Yeah, he did. He invented coverages, and he got the name from MacLane, a coverage, as a way of specifying a Grothendieck topology using less data. Okay, so what I'm describing now was invented by Johnstone, and it's a way of generating Grothendieck topologies. So we're gonna talk about all of that in more detail as we go along. But that's kind of the very main idea.
And that goes back to the earlier comment. The older definition was one where you might assume things such as pullbacks.
Right.
That earlier comment of how we got rid of that here by talking about something which, if you had a pullback, would just be refinement of it.
Exactly.
What are some nice categories that don't have pullbacks?
Category of Cartesian spaces.
Well, that depends how you define nice, because some people define nice to mean pullback, so for them, there aren't any.
But the category of Cartesian spaces does not have all pullbacks, because if you pull back by a arbitrary smooth map, and that might not be a Cartesian space. Okay. So that's going to be our main example.
Or it may not even be a manifold, right?
Well, it would be right. Yeah, if it was well, like if you have an inclusion map, then it would just be the preimage of a open subset, right? So that would be a manifold, but not necessarily. So if it was an inclusion map and you had a smooth map on the bottom and you take the pullback, that would be a manifold, but not necessarily a Cartesian manifold.
Yeah.
Okay. Good. All right. So oftentimes we think of J of U as a poset. Where R is less than T if there's a refinement. Okay? So just psychologically, it can be helpful to think of J of U as a bunch of posets, even though there does exist, more structure. Okay, so let's give some examples here finally. So our first example is the category of finite sets. Category of finite sets and functions. Now you might immediately object and say that's not a small category. You would be right, but it's essentially small. So what you can do is you can say for any finite set, I choose some representative, maybe the set consisting of 1 up to n, and then you can just consider that, and that's equivalent. So throughout these notes, whenever I say small, I typically mean essentially small, or I do mean actually small, in which case, if I say a category that's not actually small, well, just take a skeleton of it. And I'm not gonna harp on that too much. Okay. But we will be concerned later with categories that are not essentially small. Okay, so that will be important. But for right now, when I talk about small categories, I blur the distinction between small and essentially small. Okay. So for us right now, the category of finite sets is small. So I choose some skeleton of it, right? Okay. So the category of finite sets and functions has a canonical coverage on it. Let J lower epi be the collection of families on thin set where for S, a finite set, J epi of S consists of those families R Ri Si to S such that the sum is surjective. So what do I mean by this? I mean, I have a whole bunch of functions onto some fixed set S, and I want the image of those functions to cover S. So when I write the sum here, what I mean is the coproduct. Okay, so from now on in categories, sum means coproduct. Okay, so what am I doing? I take the SIs, I take the coproduct, which is disjoint union in the category of finite sets. I get a big finite set, and that projects down to S. Okay, on every component, I just do Ri. And then I want the image of all of those to cover S. That's what I mean for R to be a covering family in J epi here.
Is that just a partition of S?
Well, typically partitions require the things to be have no intersection, right? So this could have intersection. But yeah, basically a partition. So now we want to show that this collection of families is a coverage. Okay. So
if it were partitioned, this would have been not only onto, it would have been one-to-one as well.
It would have been an isomorphism, exactly. So suppose I have a function from T to S, and I have a whole bunch of morphisms to S such that their image covers S. Well, in the category of finite sets, pullbacks do exist. So what I could do is take the actual pullback of this, whoops. And now I get a whole new family. This new family will satisfy the property that the image, the union of all the images of the functions are surjective. Okay. So we call that property jointly surjective. Let me write that here. I'll write that in blue. This property is called jointly surjective, or joint epimorphism. So I pull back all of these families, I get a new family over T, and the image of those functions are going to cover T. So that means that we satisfy the conditions of being in coverage, the second condition at least, and then it's very easy to check that the identity function is a cover of S, right? So it satisfies both conditions. So J epi is a coverage on FinSet. Okay, so it's a pretty simple example. And then returning to the main example we had before, for a fixed topological space, X, we have the post set of open subsets. So now I'm going to put a collection of families on this. Let J of X be the collection of families on O of X, where R belongs to J of X U, and R is a whole bunch of inclusions if the union is U. So a covering family in J of X is just an open cover. It's the classical notion. So let's check that this is a coverage. So suppose I have V and I have it's a subset of U, which is an open subset of X, and then I have UI is a subset of U, and I have a cover of U. Right? Well, then what I can do is I can take the intersection with each of these, and I get a new cover. So given a cover R of U, get, V intersect R, which is the set all intersections. And this is the same idea as the previous one of taking the pullback, right? So pullbacks exist in this post set, and they're just given by taking the intersection like this. Okay, and then the union of these V intersection UIs over I will cover V. Okay, so this makes J of X a coverage, and hence the pair O of X, J of X is a site. Okay, so these are the two simplest examples. Okay.
Both had pullbacks.
Right. So now let me do a less trivial example, slightly less trivial. So let X be a topological space with topology tau, and let B be a basis for tau. So what does it mean to be a basis? That means that B is a subset of tau, is a subcollection of open subsets such that if B is a collection of U's, then B is a cover of X, and for each open subset U of X and little x in U, there exists a basis element. You know, I'll call these EI maybe, or maybe BX. There exists a BX containing X such that BX is a subset of U. So basis is a way of generating a topology. Okay. So now I want to show that the basis also generates a coverage. So let J of B, let J of B consist of those open covers of X containing only elements of B. Okay, so we want to show that this is a coverage. So if I have an open subset and I have a whole bunch of BIs and they cover UI, and then I take V intersection BI, there's no guarantee now that that this is that this guy here is a basis element. There's no reason why that should be true, right? There's no reason that this thing would also belong to B. So immediately it's not clear that this is a coverage, right? But for each element of V, right? So for each Y in V, there exists a basis element B of Y, and that factors through some V intersection BI, because V intersection BI is an open cover of V, right? So that means that if I take the union of these BYs over all Y and V, I get a new cover. And I get this. So if I take the collection of BY in V, and I take that over all Y and V, is an element of J B of V. It's a cover made out of basis elements. So even though when I pulled this cover back, I don't get something in my coverage, I can refine it by something that is in the coverage, in the collection of families. Therefore, I have this family, and it refines this one. Therefore, I have a coverage. Okay.
What about the other condition?
And the identity. So if you're a basis, I guess you want the whole thing to be. Yeah, you want X as a subset to also be in the basis. Yeah, that's a good point. Yeah.
But isn't the condition for every open set the identity is contained?
For every open set, the identity is contained. Say it again. If I have, so you're saying I want to make sure that
I think it's just asking you to restate the let's make sure we correctly restated the other condition, the other defining property of a coverage, right? There was the one you just checked, with this diagram, and there was the one about the whole U thing, whatever it was. So
right.
just
So if I have
make sure we wrote the right. Sure, you correctly restated that property before checking it. That's, I think, all the question amounts to.
So the point is that for JB to be a coverage, then every identity has to be in it. That would imply every open subset has to be in it. Okay. So, all right. So we found an example where we shouldn't include all of the identity families. Oh, but in my notes, I see what I did. Okay. Yeah. So in my notes, what I did was I said JB consists of all of all of these guys and the identities. So I circumvented that issue. So I just threw in all of the identities. Okay. So that's why it works. So yeah, I guess there is already an immediate example where.
Yeah. Well, by the way, this first condition has the feeling of, let's say when you're doing algebra, you might just ask your ring has an identity because I could put one in artificially if I needed to.
Yeah. So you can always just throw in the identity families. Yeah, but good point, Francis. Thank you for that. Okay. So now some more examples. So given a small category C, there are some canonical coverages. So we have J triv, trivial coverage, where for all U in C, J triv of U consists only of the identity family. We have the isomorphism coverage. Is the set of singleton families where F is an isomorphism. And then J max says the maximal coverage for all U and C. J max of U consists of the identity family and Y of U. So remember, Y of U was the maximal family. So this consists of every morphism to U as a family. And you could imagine coming up with a whole bunch of other ones, right? But as we're going to show, all of these give the same sheaf toposes. So they're all equivalent in some sense. But let me not get ahead of myself. Okay. Another example. Suppose CJ.
What if you took as your coverage the identity and the empty?
The
Or
identity and the empty family.
yeah.
That would be a coverage, right? Because if I took you and then it says for everything there, well, there's nothing there, and every morphism. Yeah, I think that would be a coverage, right?
But is it a bad, like somehow not nicely behaved because it doesn't actually cover, the empty one doesn't actually cover?
Yes. Um, so what'll happen is when you have like an empty family, um, what happens when you have an empty family is that sheaves on that object have to be terminal. Um, so like if you have a topological space and you consider the empty set as a subset, right? It's an open subset. The empty set has exactly two covers. It has the cover by itself and it has the empty cover. And it turns out that that forces when you take a pre-sheaf, in order for it to be a sheaf, a necessary condition is that when you evaluate it on the empty set, it's terminal. It's a point. Okay. And we'll talk about that more. But does that make sense? Yeah. Okay. Um, suppose I have a site. So yeah, to answer your question, is it like nicely behaved or anything? Like I wouldn't necessarily think of it as like being nicely behaved or not. It's like it changes how the sheaves have to act. Um, so like yeah, I think all the sheaves would have to be terminal, but I'm
What
not
does that
100%
mean?
sure.
What does it mean to be terminal?
It means that for every object you give a point.
Oh.
Yeah, good question. Suppose C is a site with U and C. Let C over U denote the slice category. Let J over U denote the collection of families where if G from V to U is an object in the slice, is an object in the slice, then a bunch of families let's write it like this. Then just copy this. So then this is a family in the slice over G if and only if when I project the Fi, that gives me a family over V. So what do I mean by that? So I have V to U. This is an object in the slice. And then I have a whole bunch of VIs, and they map to V over U. Call that RI. And then these guys are FI. And I say that that these cover this map if and only if when I project this is a cover in the underlying site. Okay. So let's check that that is a coverage. So if I have two morphisms, V, W, H, and I have a cover over V like this, well, since I'm in a coverage, that means that there exists a family over W, making this square commute. And therefore that gives me maps down to U. And so that gives me a family over W. Okay. So that means that J of U is a coverage. So given any site, you can take the slice and then you get an induced coverage on the slice. So those were some examples there. And now we're going to go into pre-sheaves. So a pre-sheaf X on a small category C is a functor X from C-op to set. And element X in X of U or U in C is called a section over U. If F from V to U is a map and X of U is a section, we sometimes denote the resulting section in X of V simply by X restricted to V. Okay. So this is kind of classical notation. Given a family or to UI to U, an intersection square on R, so I have I and I, so it consists of objects Uij for every pair Ij in I and maps such that the diagram where I do Uij, Ui, U, Uj, Ri, Rj, Ui, Uj commutes. So typically the way you think about this is that when you think about the open subsets on a space, if I have two open subsets and I take the pullback, then I get UI intersection Uj. But now I'm generalizing to the case of an arbitrary category where I say, okay, maybe I don't have pullbacks. Well, I say, okay, if I have any two covering maps in my covering family, I call this an intersection square. So it's any commutative diagram where I have an object mapping down to two covering maps. Okay, so it's the generalization of the intersection of two open subsets.
Right. And again, the basis of a topology looks like a good place for visualizing is you say, well, I don't have the cover, so I have to chop it up into basis elements.
Right. Yeah, exactly. Good. So that's what an intersection square is. So I've defined a pre-sheaf, a section, and an intersection square. Okay. And remember, these things here, the maps and the object here are completely arbitrary. Okay. Now.
So there's a bit of an abuse of notation right here because you may have two squares that have the same four elements, but they're, for example, the uj from one square is different from uj from the other square, even though the domain and range are the same.
Absolutely. Absolutely. Yeah.
Okay.
An X matching family over R consists of a collection of sections. I have xi in big X of ui, line I, such that for any intersection square, we have that x of little ui, write that a little bit better, and that is written like this. So what is this saying? It says, okay, I have a covering family over my U, and then for each one of those domains here, I want to have a section over UI, and such that whenever I have an intersection square like this, if I take my xi and I take my xj and I pull them both back, I get the same thing. Okay.
Hey,
And
maybe this is a bad question, but will you eventually sort of like such that the UIJs cover or something like that? Like the UIJs don't have to have any covering like property for you, right?
no,
Okay.
no, they're arbitrary.
Okay. Thanks.
Just a quick question. So UIJ need not be unique, correct?
That's right.
Okay, but it has to, there has to be, it exists.
Just has to exist.
Okay, okay, okay. All right. Thank you.
Exactly. No problem. Right. So remember, this is classical notation. What I really mean by this is this, right? So X is a presheaf. So then X of UI is a map from X of this to X of this. And then I take, it's going the other way. And so it takes a little XI in here and it gives something there. Okay. So that's what we call an X matching family. So again, this makes sense in any category. Don't have to have pullbacks. Okay.
And equality is in sets.
Equality is in sets. It's on the nose equality.
And that's why when Emil used the word set 5 minutes, pull back 5 minutes ago, because that was the pullback in set, so it was okay.
I'm sorry?
You used the word pullback a few minutes ago, but it was okay because that was a pullback in set.
Oh, I see what you're saying. Yeah. Okay. So if X is a presheaf on C and R,
You
yeah,
had pullbacks, you would only have to check this property on pullbacks, on the
yeah, we're
pullback.
getting there. We're getting there. Exactly. You're ahead of me. Yep, but that is true. Now, if X is a presheaf on C and R is a family of morphisms on U, then let match RX denote the set of X matching families on R. Given an X matching family on R, And amalgamation is what we call a global section. So the global section is the one that's on U. So global section such that when I pull back X by the RIs, we might write it as X lower UI, that's the same thing as XI. Okay, so that was a lot of definitions. Let me try and give an example. So now let's have, it's kind of annoying, X. So maybe let's do for T, a topological space, we can consider the site that we had before with open covers. Then we have, I'll call it the presheaf X is a presheaf like this, and it takes an open subset U in T and give the set of continuous functions from U to R. This defines a presheaf on O of T. And then if I have an open cover, then you can imagine I have my topological space T, and I have my open cover. And imagine it actually covers everything. I have UIs, UJs. And then for each UI in the cover, then a section would be a map Fi from UI to R that's continuous. And then if I have an intersection square, that means I have some UIJ, that's a subset of UI, subset of UJ. And then if I have for every intersection square, Fi restricted to UIJ equals Fj restricted to UIJ, then I can glue all of these continuous functions together. F on all of T to R, and it's defined by just taking a little x, and I'll just say when x is in UI, and this is well defined because if x belongs to both UI, UJ, then I have an intersection square given by the actual intersection. And I know that when I take my local sections and I restrict them to the double intersection of the open subsets, that those are going to be equal. So this is well defined. And in fact, it's unique. So for any matching family, which means I have for every UI a bunch of I have a function on each UI such that whenever I do a double intersection, they agree. That gives me a matching family on the whole cover, and then I can produce an amalgamation. And in fact, it's a unique amalgamation. Okay. So what do I want to say next? I'll say that definition. So given an object U and C, we're going to let Y of U denote the representable presheaf on U. So what does this do? So y of u is a functor from C-op into set, and it takes a v in C and sends it to the set of maps from V to U. So this is representable presheaf on U. Okay. So, and then if you have a map from W to V, that gives you a map like this, where I take a map, let's say G, and I precompose it with F, and now I have a map from W to U. Okay, so it's a representable presheaf. Okay. All right, our first lemma. So, given a presheaf X on a small category C, suppose that I have two families over U, and F defined by these is a refinement. Then if I have a matching family over R, then what I can do, an X matching family over T over T, then what I can do is I have a refinement here. So that means for every UI, I have a map to V alpha I. And then on every VJ here, whoops, let me fix that. VJ. So if I have a matching family on the codomain, then what I can do is I have for UI, I have a map from UI to V alpha I, and I can pull back X alpha I to UI. And then I get a new collection of sections, and that will be a matching family. Is an X matching family over R. Okay, so let's prove this. So let me just say one more time what this means. I say I have an object U, and I have two families over U, and I have a refinement between them. And then I have a matching family over the codomain T. I have a matching family, so I have sections on each VJ. Then what I'm going to do is use my refinement to pull back all of those sections and get a new collection of sections over U. And that new collection of sections is going to be a matching family. Okay, so let's prove that. So suppose we have an intersection square. And I'm going to draw it in a weird way. Okay, so I have UI, UJ, RI, RJ. So this is an intersection square. And so I have an intersection square, but I also have a refinement. I have a refinement of the RIs, which means that for every I have a map Fi down to V alpha I to T alpha I. And then the same thing here. I have F of J down to V alpha J T alpha J, like this. But that means that I have an intersection square with the T's. So if xj is an X matching family, then I know that if I take Fi ui of X alpha I, that's going to be the same as X Fj uj of X alpha j, because this is an intersection square over T. Okay, but then what does that mean? So that means that if I take X of ui of X Fi X alpha I, this is equal to this, and that is equal to that. So that means that for this intersection square here, when I take these elements and I pull them back here, they agree. Therefore, this collection is a matching family. Okay, so we've proven our first result. And it's a matching family over R. So that means that whenever I have a matching family and I have a refinement, I can pull it back. So we will use the notation that if xj is an X matching family on T, and F from R to T is a refinement, then let F be that pulled back matching family. On R. Okay, this makes this guy into a pre-sheaf on the category of families over U and refinements by pulling back matching families. Okay. Okay, any questions about that?
So far, so good.
Excellent.
Any questions?
Okay, so let's keep going. So, given a pre-sheaf X on a category C and a family of morphisms R on U, there is a canonical map from X of U restricted to matching family of R to X. So what is this map? Well, it takes a little x in X of U and it sends it to the collection of pulled back uh, elements, right? So if I have a whole bunch of UIs to U by Ri, and if I have a section over U, I can pull all of them back and I'll get this, right? And then you want to check that that's actually a matching family. So if I have an intersection square like this, that should be Ri. Sorry about that. Rj, Ui, Uj. Oop, damn it. And now I have this guy lives on here and similarly on there. And when I pull them back, what do I get? Well, I pull back X, Ri, X. Well, that's the same thing as X, Ri, Ui. But because I have an intersection square here, that's the same thing as X, Rj, Uj. And that's the same thing as X, Uj, X, Rj, X. Okay, so the way to think about this map is that if you have a global section and you have a cover, then you can just restrict that global section to each element of the cover. Okay. We say that X is J separated if the restriction map is injective for all U, and we say X is a sorry, we say X is a
What is
I'm sorry, say it again.
Oh, well, you just erased it, but I was going to ask what J was.
Yeah, I'm sorry. We said X is separated on R, so I fixed a family R, and I have this map, and then I'm separated on R if this map is injective, and then X is a sheaf on R if the restriction map is bijective for all.
And no name when it's just surjective?
Separated. Oh, sorry. This map is just injective, not for all of you. Sorry, what'd you say, Mahmoud?
And no name when it's just surjective?
Some people call that like an epi sheaf. What did Ben Bumpus call it? He had a paper recently where they had a name for it. It's escaping me right now. But yeah, there's some names for it, but it's not terribly popular. Okay. So what does this mean? So to be separated means that if I have a matching family, it can only have at most one amalgamation. So having an amalgamation means that I have an element X such that when I pull it back gives me this matching family. So being separated means that I can have at most one amalgamation.
Said differently, if you want to check two global sections are equal, you just need to check them locally, right?
Exactly. And then being a sheaf on R means that this map is a bijection, which means that every matching family has an amalgamation. So this map is surjective. There exists something here that restricts to this, and it's unique. Okay. So that's what it means to be a sheaf on a matching family. Now,
This doesn't have anything to do with coverages yet.
not yet. Not yet, but now it will.
Also, can I ask, you defined the category of families. So R would be an object of fam.
R would be an object of FAMU, exactly.
Um, do you define, like you defined a coverage as a certain type of collection of families, but can you define it as some sort of subcategory of fam where U varies? Is it something like that, or?
Yeah, you probably could. I don't know exactly what you would want. But yeah, I'm sure you could repackage it somehow.
Emilio, could you just spell out what structure is being used to define what a sheaf is?
The structure that's being used, well, so I'm talking specifically about a sheaf on a specific family.
Sheaf on a specific family.
So far, I've only defined a sheaf on a family, on a
You
single
haven't
family over a
defined what
single
a
object.
sheaf is. Yeah, I see.
Yeah, right. But now, if I have a site, so let me draw a line here. Now, given a site, I call X a J sheaf if, and J separated also, same thing. I called X a J sheaf if X is a sheaf on every covering family R in J. So in particular, by my remark above, that means that for every covering family over every object, X has to be a sheaf on that covering family. So I'm quantifying over every covering family over every object. Okay. So that's what it means to be a J sheaf.
So above R was just a cover, right? I'm
Yeah,
sorry, it was a family, right?
a family.
A
Now
family
we're
doesn't have
restricting.
to be part of anything.
Yeah.
This is
Now we're,
a collection of morphisms.
yeah, yeah. And now we're going to restrict only to showing that it only has to be a sheaf on the covering families in order to be called a J sheaf. Okay. Okay, good. Um, definition.
And a covering family means a family belonging to a coverage.
So being a covering family, if R is a covering family, that means it belongs to J of U, where J is a coverage.
Yeah.
Right? Oops. Okay. Now, given a site, um, uh, let this category be the full subcategory of the pre-sheaf category on the J sheaves. So I didn't say this before, but if I have a category C and it's small, then I get a category of pre-sheaves on C whose objects are pre-sheaves, and then morphisms are natural transformations. Then I let this category denote the full subcategory of the J sheaves. So morphisms are still natural transformations. Okay. We say a category E is a Grothendieck topos if there exists a site CJ and an equivalence. Okay. So that's what we mean by a Grothendieck topos. Now, it should be pretty clear that every pre-sheaf category is a Grothendieck topos. So let's prove that. So what do I want to prove exactly? So let's consider maybe J triv on a category. C, so this, remember, was the coverage consisting only of identity maps. And I want to show that every pre-sheaf is a sheaf on this site. So lemma, given any small category, C, every pre-sheaf, say J sheaf, say J triv sheaf. So what do we have to prove? We have to prove that, so suppose I have a matching family. Okay, let me start over. So what does JTriv consist of? So for every object, JTriv consists only of the identity map. So an X matching family consists of an element, consists of a single element, X, and X of U, such that for every intersection family, so that means for every, I'll just denote it actually by W, and these are arbitrary maps, U and V, but of course, if this diagram commutes, then U has to be equal to V. So this means for any map from W to U, it has to be the case that X of U of X equals X of U of X, which is obvious, right? So that means that every matching family has a unique amalgamation given by itself. Unique amalgamation given by itself. So therefore, if I take sheaves over a category with J triv, that gives me just pre-sheaves. Okay. So every pre-sheaf category in particular is a Grothendieck topos. And similarly, you can also prove that the other sites I talked about also have this property. If I do J iso, if I do J max, these are all pre-sheaf toposes. Okay. So I've got what, like 20 minutes left, Mahmoud?
Yes.
Okay, so let me.
Can I ask one kind of
Yeah.
global picture question? So previously, classically, you have definition of category and pre-sheaves of sets.
Hmm.
Then you talk about Grothendieck topologies, then you define sheaves, then you define a topos to be something that is category of sheaves on some Grothendieck topology, right? So now you're defining what a sheaf is using less structure than a Grothendieck topology, or let's say a different structure than Grothendieck topology. Question: have you created new sheaves, or have you created things that weren't toposes and now they are toposes? Or
So later, maybe hopefully next session, I'll prove that every coverage completes to a unique Grothendieck topology, and the sheaves on the Grothendieck topology are the same as the sheaves on the coverage.
okay,
So we have not created any new sheaves.
Right. So in this case, it really does, and really does generalize the whole idea of that basis example.
Exactly. Exactly. Yeah. Yeah.
but the notion of Grothendieck topology, did that require the categories to have pullbacks?
No.
No.
So I'll say maybe next
But
time what a Grothendieck
some
topology
books
is.
assume that, don't they? Or
So that's what they typically call Grothendieck pre-topology.
ah,
So in that case, you do have to have pullbacks in the category of those maps.
ah.
Yep.
So I see. So not all Grothendieck topologies come from Grothendieck pre-topologies because
That's right. That's
require
right.
pullback. I see.
Well, see,
So a
from
Grothendieck topology may
Grothendieck,
not be a Grothendieck pre-topology.
a Grothendieck topology is almost never pre-topology.
Ah,
Yeah, it's terrible terminology. It's really crazy. But yeah,
all right.
Yeah, and even going back to it, the term topology isn't so great here either, for that matter.
yeah,
I mean,
yeah.
it just goes back to, yes, the 40s when people were just figuring this out and didn't really understand it, and the words stuck around.
Yeah. Okay. So, yeah, I don't want to do too much. We only got 15 minutes. So let me just say the one thing that Francis already figured out, which was that if I have a site and C has pullbacks, then then I have a bunch of sections uh, is an X matching family for a covering family R and J of U, if and only if we check the condition only on the pullbacks. So now I don't have to check every intersection square. I just have to check the intersection squares of this form. Right? So why is this true? I'll just give a quick argument, right? So suppose I have an intersection square, then I get something like that. And then by the universal property of the pullback, I get a dotted map like that, such that everything commutes. So if I have two sections here, I want to check that when I pull them back to there, they're equal, right? Well, if I check on the pullback that they're equal, then to pull it back here and pull it back there is the same thing as pulling it here, pulling it there, pulling it here, pulling it there. So if they agree on the pullback, you're done already. Okay. So Grothendieck pre-topologies are very nice because you only have to check the matching condition on the pullbacks. Okay. I hope that made sense. Okay. And then I'll do one more thing and then maybe we'll stop after that. Um, So now I want to compare two coverages on a category. So given a small category C and coverages J, J prime on C, we write that J is a subset of J prime if for all U in C, J of U is a subset of J prime of U. And we write J is less than or equal to J prime if for all covering families in J prime, there exists R in J and a refinement. So what is this saying? It says, okay, so suppose I have some coverage and I have some covering family. I want to know that there exists something in the other coverage that refines it. If so, I say J is less than or equal to J prime, or I say that J refines J prime. Okay. And then these have some very simple consequences. So given coverages J, J prime on C, we have if J is less than or equal to J prime, then sheaves on C with J are sheaves with on C with J prime. And if J is a subset, then sheaves on J prime are sheaves on J.
In the first condition,
Yep.
it's literally every uh, family or covering family in JU is also in J prime.
Exactly.
Whereas in the second one, if you have an R in J prime to view, there's an R prime to J prime to view, then there's a refinement in J of U.
So think of it like I have maybe a manifold and I have a good open or say I have a manifold and I have an open cover. I can always refine that open cover by a good open cover. Okay. So therefore, the coverage of open covers gets refined by the coverage of good open covers. Okay.
Is it a different notation for 1 and 2?
Yeah, I swapped them. Whoops. Well, I'll just leave it. Sorry. Um,
One of them is like, what is the difference between the notation?
whoops. Yeah, they're kind of similar. Subset less than equal to,
Okay, thanks.
right? And then subset and then less than equal to.
But then on the other side, the prime switched, huh?
But then they switch, exactly. So let's see why that's true. Um, so let's prove 2 first. So suppose that every covering family of J is a covering family of J prime. Then to be a sheaf on J prime, you have to be a sheaf on J and more, right? Because to be a sheaf on J prime means that for every covering family in J prime, you have to satisfy the descent condition for that covering family. But there are more here. So therefore, it's harder to be a sheaf on J prime than it is to be a sheaf on J, right? Um, so that's 2. And now 1. So let's argue for 1. So let's see. So if I'm a sheaf, so suppose is a J sheaf, and then I have a covering family R prime and J prime of U. I want to show that X has descent with respect to R prime, which just means that every matching family has a unique amalgamation. Um, well, um, there exists an R in J of U and a refinement. That's what we assumed. Now, it turns out, so I didn't get to write this down, but I'll write it right here. So such that F is a refinement, then if X is an amalgamation for the pullback of some matching family, then it is an amalgamation for the original matching family. Okay. Oh, that's not what I wanted to say. Okay, I'm sorry. That's not what I want to say. Apologies. So this we'll have to prove next time. So let me write that like this. So prove next time. The statement is if X is a J sheaf and R is in J of U, and there's a refinement from R to R prime, then X is a sheaf on R prime. Yeah, okay. From this, you can deduce this. Okay. So the point is, if I can refine everything in J prime by something in J, then every sheaf on J is in particular sheaf on J prime. So in the example from before, if I take open covers and I take good open covers, then every sheaf for good open covers is in particular a sheaf for open covers.
In that case, you also have that the good open covers are also covers, so you get equality.
Exactly. Yeah, because it also satisfies this.
In the
right?
opposite. Yeah.
In the opposite direction, where like this would be good open covers is actually a subset of this. So then you got the opposite inclusion as well. Okay. So I think I'll stop there for today.
So it's good. It seems to be a good set of lemmas for showing that when two notions of sheaves are the same.
That's kind of the goal of a lot of this. So I'm not going to be proving any really crazy theorems. We'll maybe talk about Giroux's theorem later on, but the whole idea of these notes was to kind of give glue and give additional little lemmas and fill in folklore that experts in the subject know, but don't appear so easily in the literature. So I wanted to just give a kind of well-rounded foundation to all of this stuff.
Well, these are great sets of notes. This is great service, and your pace was just perfect. It was good.
Awesome. Okay, good. Are there any questions?
Any questions?
Well, I do have one. It's not directly to this talk, but I was just curious because, a few months ago, you and Matt were doing this thing where you were trying to tie it up with operads and all that. Just wonder if you ever got back to thinking of that project.
Yeah, so okay, so what I'm going to do next time is I'm going to describe uh, two different ways, two conditions that a coverage can satisfy, called refinement closure and composition closure. If it satisfies these two conditions, I call it a saturated coverage. Okay. Now, the composition closed coverages are ones that have like an operad structure. So if I have like a covering family, I can imagine sticking another covering family on one of the objects in the domain. And then I want that composite to now be a new covering family. So in that sense, it is like an operad. Once you have a coverage, it makes sense to say that you can just stick these families. I mean, you don't even need a coverage, right? If you just have a category and you take families, and then you can stick families
Right.
to domains, and you get something like an operad. But if I remember correctly, there was a problem because these could be infinitely wide, right?
Okay.
So typically an operad only allows you to have finite amounts of input for operation. So these would require infinite ones.
Yeah.
And maybe Matt can correct me, but I think there was like some definitions we had seen in Leinstrom's book that uh, should have
I
covered this.
remember from when I was going down that rabbit hole with Matt, a lot of it to me seemed because when people define their opera, they're not thinking the infinite things. They simply assume, well, I can just order the things, as opposed to maybe having to explicitly index them and keep track of that. And there's
Yeah.
some other issues. I remember that, part of it really comes down to it looked like you could modify definitions that no one ever thought of it because they were never, running into cases like this where they'd have to have infinite things.
Yeah.
Or at least that was the overall impression I got.
Right. Yes, I don't know exactly what we should call them, but they're basically opera. You basically
Okay,
get.
yes. Yeah. No, I was just wondering because I remember I spent about 3 hours with Matt and I think someone was sitting John and talking about this. So just
Okay,
curious.
I see. Okay, so
No
next
worries.
time, what I'm going to talk about, what I'll do is because I didn't get to cover very much today, so I think next time I'll go at a little bit of a faster pace. And next time, what I'll do is I'll talk about these closure operations, refinement, composition, and also talk about sieves, composition, and sifted closures. I'll mention Grothendieck topologies, and I'll prove that there's a bijection between Grothendieck topologies and what I call saturated coverages. I'll also talk about local epimorphisms, because you need to talk about this. And then I'll also talk about some set theory. And then maybe after that, and maybe if we have time, I'll do examples of sites and toposes that'll be interesting to this audience. So maybe complex manifolds and manifolds. Yeah.
And what about the time after?
And the time after, well, we have to see how much we get through of this. But the time after, so next time, I would love to talk about morphisms of sites, and locally presentable categories, and Giraud's theorem. But I will say that, this part here requires a good deal more category theory than today or next time. So I'm just warning everyone that
So that might be more of a Wednesday talk than a Friday talk.
This is much more of a Wednesday talk than a Friday talk, exactly. So yeah, this last one I'm gonna have to really give him some details.
Are we going to learn about hypercovers too?
No, unless you want a fourth one.
Maybe say possible fourth one.
Possible fourth.
Sometime in the summer.
Okay. Possible fourth talk. Hypercovers.
Ouch.
Yeah. So that'll be fun. Yeah, but I'll try and go at the same pace for next time. I'm gonna skip more of the proofs, so I only had some very simple proofs today, so I wanted to show those. Always show like at least one proof, right? Next time we're not gonna go through most of the proofs. They're quite tedious and simple. But I'll still try and cover all of this stuff.
Well,
All right.
covering everything is very important in this topic.
When is next time? Is it next Friday?
Next Friday. Same time.
Yeah. Thank you. It was very good.
Thank you. Any other questions?
Brought back a lot of memories.
Any questions? Okay, I'm gonna stop the recording.